Okay, welcome to the sixth lecture of the EECE574, the graduate level probability and random processes. As announced last time, quiz 1 is coming and it will be taken on next week, Thursday, during the class meeting hour. It will cover up to Tuesday's material. It will take up 10% and it's an open everything course, everything quiz. However, you cannot communicate with any other person. Homework 3, of course, will be assigned today or tomorrow. Handout for chapter 3 is updated, but only first a few pages. So pages 3-9 to 3-11 are changed. By the way, what does this PP dot mean? Pages, okay? If you just use P dot, it means page. And if you use PP dot, it should be read as pages. Got it? So whenever you cite a reference paper in your thesis or something, you have to read some authors have written this paper, blah, 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 and it's in volume number 7, pages 1 to 5, something like that. Passwords are, as you know, the lowercase numbers like ONE, TWO, FIVE, something like that. Recorded class meetings are sequentially uploaded to the CISL Postec YouTube channel. And if you have time, please place clickable timestamps so that people who will take later can be benefited from your little effort. I always have message as a graduate level courses instructor. Whenever you want to solve and understand something, my two advices are simplify and visualize. Especially, I mentioned about the lessons obtained from great inventions, and they usually replace a scarce resource with an abundant resource so that they could solve their problem without introducing too much cost. And sometimes they add two separate inventions to have a new invention. Sometimes they remove something to make lighter, to make it less costly. Sometimes they put same thing several times, millions times, and it really helps sometimes. And sometimes you divide some component and make them smaller one, many of smaller one, that gives you a lot of new benefits, something like that. Russians, especially the Soviet Union Russians, were very colloquial Korean says 진심이었다. They were really eager to theorize everything. So they invented a theory of inventive problem solving. And if you are interested to be taught about trees or its related afterwards theories, please search Professor Youngtaek Park at Sungkyunkwan University or creative thinking in KMOOC or YouTube. I have checked that his KMOOC lectures are still available. I really love that and enjoy it, although it's more than 8 years. Okay, here goes the overview of this course. We are reviewing the probability and random variables part. We finished probability part and we started random variables part. Last time, we learned a lot about the expected value of a random variable. Unlike what you learned in your undergraduate or high school math, I used measure theoretic definition of the expected value of a random variable. So let me remind you. what was that? So yeah, this is a kind of measure theoretic definition. Expected value of a random variable x. Sometimes people love curly brackets. Sometimes people love square bracket. Let me use square bracket. And it's defined as what? Summation of the value times probability. Here, S is an outcome of the outcome of an underlying probability space. So it's a member of the sample space. So this is the definition. And since you haven't taken the measure theory course, 측도론, so this does not mean much. However, it is very useful to derive one of the most important property of the expectation operation. What is it? Expectation is a linear operator. What does that mean? Suppose you want to compute the expected value of a new random variable, constant times x plus constant times y, where x and y share the same probability space, which means that they have a common probability measure. However, they are different functions that admits sample from sample space and generates possibly different real numbers. Then, applying this definition, this expectation is nothing but a times x of s plus b times y of s. And this becomes the integrand of the expectation. And you integrate this integrand with respect to dp of s, where p is the common probability measure, because you have only one probability measure. And then we use the linearity of the integration so that we have a times expected value of x, b times expected value of y. So we have a linearity. For constant case, which is very special, we have the same value. So constant random variable, which is a kind of degenerate random variable, has its expectation the same as its original value. By the way, our plan today is to move on to the transformation of a random variable. What's the difference between expectation and this transformation? The commonality first is that your input is random variable, and you get, in this case, a real number, a deterministic real number, if it exists. Sometimes the mean of the random variable does not exist. So existence not guaranteed. The second topic is something like this. You have now a deterministic function g, okay? And then as the input to this system, you have a random variable. Then what would be the output? And how can you describe the output? That is the main of today's topic. But let's finish up our review first. So we just recalled our measure theoretic definition of the expectation of a random variable. Here, I emphasize two things which are quite different from our undergraduate calculus or probability course, because I emphasized as just this expectation is not guaranteed to exist. Why? Because even though this dps is always non-negative because it's the probability match, it's the derivative of how to say it, kind of derivative of probability measure. So this is non-negative. However, this value depending on s, can be positive and negative. So in order to compute this integration, first we need to define the positive part of the function and the negative part of the function, which is still positive, non-negative, and subtract them. Now, this x plus is always non-negative. This integration either exists as a finite number or positive infinity. And the second integration, because x negative of s is also non-negative, you either have a finite number or plus infinity. Either first integration is infinity or second integration is infinity. Our subtract difference does not exist. So this integral, the expected value of a random variable, exists if and only if your positive parts integral is finite and negative parts integral is also finite. Here, I myself was also many times confused because it seems that it sounds like negative part of a function must be negative. However, we don't define that way. So we define x plus of s as max of x of s comma 0 or x of s plus absolute value of x of s, or in current popular fancy way, ReLU of x of s, something like that. Similarly, you define the negative part as still you use max. You still use something plus its absolute value, and you still use ReLU of something. The difference is what? Here, you take negative of x of s and still 0. Here you use negative x of s. Here you use negative x of s. The reason why here in our handout, I dropped the minus operation, negative sign is that the absolute value of negative something is same as the something. And here you have ReLU of x of s. And by the way, this max of something comma 0, this operator, that operator, or can be seen in this way. So here goes x. You have ReLU. Then output is what? If you plot its graph, it looks like up to the origin, its value is 0. And the positive part is x. Okay, so it's a nonlinear activation function. And as you see that, if you subtract these two, these parts cancels, and these two terms add up to 2 times x of s. You divide by 2 to get the original random variable. So whenever you add up countably infinite or uncountably infinite, positive and negative terms, be careful. You have to kind of sort them into 2 groups first. Hey, positive things come here. Hey, negative things come here. And then you add up and check whether it's finite. You add up, check whether it's finite, both finite, and then add. Of course, if you already reverse the sign, subtract, then you have the integral. This is also actually true for Riemann integral. So this positive and negative parts thing always applies to the Riemann integration as well as the Lebesgue integration I'm going to review. The problem of integration, the Riemann integration, is the kind of very vividly shown when we have this strange function f of x that takes value 0 if x is irrational and in between 0 and 1, and 0 if it's rational and in between 0 and 1, and elsewhere, something like that. But anyway, what we are going to do is the integration of this function. And according to our Riemann integration, what we do is that we consider dividing the integration interval into finite number of non-overlapping intervals. When they add up, they become this interval. What we do is that we find the minimum value and maximum value in each interval, and then multiply that value to the width of each bin. So we take maxes, we take mins, and then add up, and we have the lower bound called the lower Riemann sum, and we have the upper bound called the upper Riemann sum. And then what we do is that we increase the number of bins. At the same time, we must shrink the maximum interval of each bin. And then if we again apply this idea and existence, blah, 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 then what happens? This lower Riemann sum may converge. Upper Riemann sum may converge. I'm not saying it always converges. So under the assumption that the both converges, and if they are the same, we then say that the Riemann integral exists. So this story was taught when I was a freshman, when I took the calculus 1. However, at that time, I could not understand the importance of this definition. I just regarded that, hey, what does my professor is talking about? We learned about calculus. And suddenly, in several years, I found that even at that time, the fundamental theorem of calculus was not carefully taught in our high school math course, even though it was stated. The fundamental theorem of calculus is very important, and that requires the knowledge of the definition of the Riemann integral. But anyway, at that time, we just relied on our intuition to define the definite integral. And a few years ago, I found that in the last revision, not the most recent, the last one, actually last one, the last revision by our Department of Education on high school math, taken that fundamental theorem of calculus out of the curriculum. So the high school textbooks were defining the definite integral, the finite integral from A to B as what? Inverse derivative evaluated at B minus A, something like that. So I was shocked. Anyway, so remember this one. Now let's apply, go back to this problem. If you calculate the lower Riemann sum is always 0, because for any interval, your minimum value is 0, because you can find at least one rational number. Your upper Riemann sum is always 1, so they are different. So in this function, given this function, you don't have the Riemann integral existent. However, in the Lebesgue integral, in order to circumvent this kind of problem, because definitely we have uncountably infinite number of irrational numbers and countably many number of rational numbers in this interval. And as far as you can just remove 1, you know that removing, for example, 1/2, if the function value is always 1, and you just take the function value at 1/2 to 0, it does not change the Riemann sum, Riemann integral over the area, right? Now you take another one, it does not change. You take another one. So it really appears that even if you take countably infinite number of values and set the function value 0, the area must be 1, because you still have uncountably infinite number of irrational numbers. That's the idea of the measure theory. That's the idea of Lebesgue integral. So what they do is that they just divide the y-axis. However, as I told you, they are not computing something like this. What they do is they find whether each interval has some point where you can find the corresponding value of x. For example, in this interval, there is no x that gives you some value near this y value, right? So it does not contribute. However, in this case, now you have what? The entire interval from 0 to 1 for irrational cases corresponds. And then what you do is that you define this integral, in this case, as what? 1 times the measure of this one. And what is the length or measure of this one? That's 1. So your Lebesgue integral of this function on the interval 0, 1 is 1. And what is the most important result we do not prove? If the Riemann integral exists, its Lebesgue version, Lebesgue integral, also exists and the same. However, the converse is not true, as we've just seen. Even though the Lebesgue integral of a function exists, the Riemann integral may not exist. So mathematicians successfully generalize the Riemann sense of integration, because if the Riemann integral exists, Lebesgue integral exists and has the same value. Anyway, now, given our first definition, which is very in-depth, we don't want to use this one because as far as a random variable is concerned, we don't need the sample space and event space. We just need what? The real number as the sample space and the Borel sigma field as the event space and the induced probability measure as the probability measure. So here, let's use R and Borel sigma field and Px, the induced probability measure. Now, definitely, the expected value must be rewritten as what? As the, in terms of this induced probability measure, and we can easily show that this is, sorry, x. We can write it this way. And also, we know that this P of x, the induced probability measure, evaluated at the interval -infinity to some x equals to the CDF. So we have the definition of the expected value of a random variable in terms of the CDF of our random variable. And this integration is called the Stieltjes integral. And I don't know why this is pronounced as Stieltjes, but probably Dutch or I don't know, that area people. So it's not Stieltjes. Anyway, about the Stieltjes integral, we also have 2 versions, Riemann Stieltjes integral and Lebesgue Stieltjes integral. And you study yourself about that because this is not a real analysis course. Anyway, so this is a kind of the ultimate definition in this course because we want to avoid the major theoretic thing as best as possible. So this only involves the CDF. Now, one good thing is that this definition includes 2 special cases. What? The first, when x is a discrete random variable, we can show that this formula becomes what? Sigma x in the range of the random variable. And the summand is what? X times the probability mass function of x evaluated at x. You know very well from your probably the first course in probability and random variable. Probably it was a middle school math or a high school math. Second, if you have a continuous random variable x with PDF well defined, that well depending on your mathematical level, because in your high school there was no direct delta function, so your PDF was probably very, very smooth. But after you learned the direct delta function in signal gen systems, especially in electrical engineering, you now just use direct delta functions. So you can actually handle a mixed random variable. So in case you have a continuous random variable or a mixed random variable, what do you have? Because the density function is defined as the dfx dx, you can replace this one as density function times dx. So you have two old friends you learned from your high school math. Got it? So that is the story, probably much different from what you learned so far in other courses. We covered the linearity and we covered the special case of expectation. Now here goes the preview. I'm going to use the indicator function again. I told you indicator function is a very useful function, and you can make a lot of derivation very, very simple. You don't need to do some kind like if this condition satisfies, then this is the answer, otherwise something. Whenever you have either one or the other, you can use the indicator function. In that case, you can simply write two if, then else if to a single formula. Got it? For example, let me show you how I can write it. This is exact example. Let me show you. F of x equals, you do it, 1 sub something of x. What is this something? Yeah, very simple. So Q complement intersection 0, 1. Right? So if x is a member of this set specified in the subscript of the indicator function, then, hey, 1, otherwise 0. Right? Of course, in this case, let me use, yeah, probably I have to write carefully like x not in 0, 1, probably. Anyway, so you see the power of the indicator function. Anyway, and then as we've done in our probability theory part, not only we have a probability space, we can have a lot of kind of derived probability spaces called the conditional probability spaces. At least we are, if we are given a single probability space, right? So again, we do almost the same thing. Now we do is that conditional, we consider the definition of conditional expectation. And again, we do total expectation theorem, as we've done total probability theorem. And here goes the fundamental theorem of expectation. And that is related to what? Oh, okay. Anyway, there are too much things, so let's directly use our lecture note. So this is the thing. So given the probability space and an event, can you rewrite the probability of event A in terms of expected value? By the way, you have a random variable x. let me not use random variable. So you introduce some random variable x, and can you rewrite the probability of the event A in terms of the expectation? Can you do that? So my question is, find or construct the random variable x so that expected value of random variable x is the same as the probability of this event. You remember? To define a random variable, we must assume there exists some so-called underlying probability space. So I've given you the probability space. And my question is that if I take an event from this event space and I want to find the probability of this event A, and can you give me, or can you define a random variable x so that its expected value becomes this probability of event A? And my hint is that use the indicator function. So what is your answer? So you understand my question? Answer, let me give you. Unfortunately, this is a mass production line of education. I'm not your private tutor. So x is simply A sub, 1 sub A of S. Why? Let's see. So according to this definition, you have 1 sub A, right? Now, what is this one? Let's use our definition. 1 sub A of S d P S. Now, let's consider every possible S to compute this integral. Whenever you have confusion, rewrite it as a summation of what? Summation of the value times probability. And this value is either 0 or 1. When do we have 1? If it is 0, what happens? We can ignore it, right? Because we have the product between the value and probability. If value is 0, that term does not contribute. So what? You have 1 times plus 0 times S not in A. And this is, whatever this is 0, right? So the second term is 0. And what is the first term? This is simply probability of event A, right? So by using the indicator function with subscript the event A, you can link the probability measure and the expected value of a random variable. And you may say that, hey, this is just a small trick. I was not taught this trick in my other courses. Yes, but this is very important. One of the very interesting part is this one. Probably you remember the theorem, so-called the inclusion-exclusion principle or lemma or theorem. What is that? It is usually taught in the probability part of the probability and random variables course. Suppose you have a random experiment and events A, B, C, or A1, A2, A3, A sub n. And what do you have? Your question is something like this. What is probability of A union B union C in terms of probability of A, probability of B, probability of C, probability of A intersection B, B intersection C, C intersection A, and A intersection B intersection C, something like that. How did you find this one? Of course, you use the Venn diagram, right? So we were taught from our high school math that here is the sample space S, and we have the event A, event B, event C, and your teacher or professor said that, hey, think about the area of this in union. And then this area is what? Area of A plus area of B plus area of C, and then you subtract the A intersection B, B intersection C, C intersection A, and you suddenly find that this all intersected one is subtracted once more, so you add up something like that, right? So you got the answer. However, when this is generalized, what do you have? And you said that, okay, if you give me the answer, I can use the mathematical induction. And you may say, and you never tried. Your professor or teacher just said that I use mathematical induction, you can do. Actually, it's very difficult. So how do we solve this one? The trick is that you introduce random variables. What kind of random variables? Indicator function with subscript something. For example, let me simplify the problem, okay? What is this one? As an expected value of something. You never thought about this, but now you know A intersection B, right? Now, can we do something more about this one? Because this means that if S is E as a member of A and a member of B, this is 1. So you can suddenly say that, hey, it seems that this AND operation can be written as what? Product of two indicator functions. Amazing, right? Now, what about the union? Then what can you do? As you've seen here, using intersection and replace it as a indicator function, product of indicator functions is very, very good trick. So what do we do? What we do is that we do this, right? It's from what? De Morgan's law, right? And then what we do is that and then what? And then what? You just expand, right? So what you have is amazing, right? So now you can do the generalization for this kind of thing. And I will just let you think about that after this class meeting. Anyway, so even though I just put a single line saying that, okay, indicator function relates probability and expectation, actually you have a lot to discuss. Got it? Now, the conditional expectation. And again, this conditional expectation also requires our use of indicator function to make the expression very, very simple. So let's do that. So we have the underlying probability space and a random variable x. Of course, we want to select an event A in the event space. Otherwise, we cannot construct the conditional probability space. We may say that, okay, we have the same thing. What is the conditional probability measure? And as you remember, this is something like this, right? So this is your original probability space and random variable x and event A. And this is the conditional probability space with sample space, event space, and new conditional probability measure. Am I right? We've done this already. Now, you still have the same random variable x. And my question is, what is the expectation now? And what would be our, so here you have the expectation, right? Now, given this probability space, conditional probability space, still you want to compute the expectation, but what would be a good new notation? Okay, so unlike your previous courses, I'm going to really encourage you why we have this notation, okay? Because most of the courses just give some notation as a definition and does not motivate you a lot. And when I was a student, I really hated that because I always thought that whenever we define something, there must be a good reason or at least justification. What people have invented is this. Okay, as motivated by this notation, why don't we use notation something like this? So expectation of random variable x conditioned on the occurrence of the event A, which makes sense. Got it? Now, suppose we just are given a random variable x and some event A, and suddenly somebody have given you this notation. What that must be meaning this one. You implicitly derive the conditional probability measure, and using that measure, we may say that measure is Q, right? As we say P, that can be say Q, and this may be defined as what? Integration of S in the sample space, X of S and dQ of S, right? Same thing. But fortunately, we know all the story. If we define the expectation in terms of some probability measure, we don't need that. We can use induced probability measure. We don't need that. We can use the CDF. What is CDF? Conditional CDF. Conditional CDF of random variable x. So we need to define the conditional CDF, and which was done already, right? So after that, we differentiate, and if we have the conditional density of random variable x given the event A, then this is our conditional expectation. Done. Okay. So do you get the idea? Now you may say that, wait a minute, you said you are going to use the indicator function. Where is your indicator function? Actually, here it is, because what is this one? What is this conditional density? What is your conditional CDF? If you remember correctly, conditional CDF is defined as, so you yourself remember, but let me give you, I need a space, just a second. I need a space. It seems that I'm talking too much, and I hope we can start our random process part. I'm scared already. Just a second. Okay, I have the space. So conditional CDF first. So what is this one? Probability of capital X less than or equal to X given A, which is probability of A and probability of X less than X and X in A, right? Got it? And this is a strange notation, of course, very abused. So what can you say about this? X in the interval infinity X, right? And X in the set A. Of course, this X in the set A is very confusing. But anyway, let me do this. So what is this one? This is probability of something intersection, right? And you've just seen there. You can replace the joint probability as what? Expectation of indicator function of the intersection. And indicator function of intersection is product of these two. So what do we have? Let me jump, and suddenly you have just a second. Just a second, just a second. X in A, X in A. Yeah, something like this. Got it? So you have the CDF of X, indicator function of X. Okay, I hope I'm right. And then your density equals, I hope I'm right. Yeah, something like this. Yeah. Anyway, so you can use indicator function. By the way, what does this mean physically? I motivated you that the expected value of a random variable is closely related to or strongly or directly motivated by the notion of center of mass in physics, right? Then what is the conditional expectation? So let's go back to our physics course. Suppose you have some planar object with the center of mass here. Got it? You somehow computed that. Now you divide it into two. And let's say this part is A and this part is B. And what was the most interesting result? I still remember I was very shocked when I was first taught about this one when I was an elementary school student. My teacher just gave the answer. What was that? You just compute the center of mass of part A and assume that all the mass is here. I focused. All the mass in A part is focused here. And you compute the center of mass of B, and all the mass in part B is concentrated at that center of mass. And what you do? You just compute the center of mass of these 2 points. Then, okay, something's not correct. So let me little bit move our original center of mass. It should be, yeah, something like that. And she just told us to justify why, given a triangle, the center of triangle lies on the what? Line that connects this, right? The question was that why the center of mass of any triangle lies on this straight line that bisects this BC. And her justification was this. Hey, Junho, consider a very small strip. Where is the center of mass? I said, here. Consider this small strip. Where is the center of mass? Here. Consider here and here. Now you compute the two center of mass on the straight line. Okay, so suddenly, she said, that's why the center of mass must be on that straight line. And then she also told me, okay, now you do the same thing for this segment AC. So you do the same thing. And your center of mass must be on this line. And she also said that you do the same thing for the segment AB, and you have that. And there was really questionable statement. These three lines intersect at a single point. And she said that that's the point of center of mass. You remember that, right? You suffered the same question. Anyway, now forget about the proof of that. If you are interested, just search for any video on the YouTube. There are tons of videos half made by Indians, especially IIT undergraduates for their projects, or IIT would-be student, high schoolers. Okay. Anyway, tons of. So what's our interpretation of the conditional expectation? It's like this. So the expectation, right, of a random variable can be rewritten this way. See that? This corresponds to the partition ith partition's center of mass. And what is this? The mass, right? The location of the ith center of mass and its weight, right? That is exactly you computed center of mass of 2 points. One is located at x1 with mass m1. The other is located at x2 with mass 2. What was the center of mass? x1 times m1 plus x2 times m2 divided by m1 plus m2. And this mi divided by m1 plus m2 corresponds to the probability. So what? This is called the total expectation theorem. Exactly can be interpreted to that physics or elementary school math thing. Okay, I'm not going to too much delve on it. We are running out of time. What is the fundamental theorem of expectation? So here we have a big division first. It's like this. As I told you, we have some deterministic function g, and we have a system, right? Every mapping rule can be viewed as a system, especially here, since the mapping rule admits a possibly real number and generates a real number. We have scalar in, scalar out system. Now, we are very familiar with the case where the input and outputs are deterministic numbers. However, what if we have a random source that generates a real number with uncertainty? So we modeled it as a random variable. Now we serially connect this function and observe the output. So my first question, and you are also asked in your undergraduate probability and random variables course, is what? What is the output of this system? How do you mathematically model the output? And your answer was what? It's a random variable. Why? Why the output is a random variable? Why? The first intuitive approach is that you put them together. And let's say this as a new source. Then what do you have? See that depending on the realization of x, your output varies. So your output is a real number if G is a mapping such as R into R, then you have a real number output with uncertainty. And definitely that must be modeled as a real random variable. So let's say output is Y. So Y is some random variable. And what would be our best notation for Y in terms of X and G? You never thought about it because you were just given in your undergraduate course as this. Actually, this is a notation, right? It's not just trivia. This is a notation of this situation. Okay? This is a notation. So whenever you see some deterministic function whose input argument is a random quantity, remember this block diagram. This is very important later. Okay? Anyway, so given that, since we were thinking about the expected value, my question is, what is the expectation of Y? And by using this new notation, we may put that notation into the argument. So our question is this. Sorry, X. And according to our definition, let's focus on the left-hand side. What do we need? We need to derive, for example, the new probability space and probability measure. And probably we do something like this, right? Do we need that? Or at least we have to derive the CDF of Y and compute this Stirchus integral, or hopefully the density function. We don't know how to derive yet, how to derive the density function of a function of random variable. The fundamental theorem of expectation says that, hey, you don't need to derive this density. Just use this one if the PDF of X exists. Unfortunately, as I just told you in the beginning of this class meeting, that even my high school textbook just provide me the fundamental theorem of calculus. The fundamental theorem of expectation was just given as a definition in many lower level undergraduate textbooks. Actually, it's not. It has to be proven because it's a theorem. Okay, so this is the definition, but we must be able to prove that that can be rewritten this way in terms of the PDF of X or CDF of X. No textbook proved probably. I'm not going to prove that either. Okay, I just want to let you know that that was not definition. It was not trivial at all. It must have been proved. And this motivates us a lot of interesting things. What? See that? Here, see the notation. Sometimes notation gives us how to memorize some interesting, important theorems. See that? Here, what is deterministic and what is random? Of course, you may say that Gx as new random variable Y is random thing inside the expectation operator. However, you can say that, wait a minute, X is random thing, and I know the distribution of X. Then you don't need to compute the distribution of this Gx. You still use distribution of X, and your expectation definition is modified in this way. G of, now you change this, because that was just notation, as a free variable or dummy variable, X in this case, and the density of X, if density exists, or if CDF, if you want to CDF, D CDF. Got it? So this is the power of this theorem. It's not definition, it's theorem. Even I do not prove. Now we define the moments. Why did I presented you the fundamental theorem of expectation first? Because moments are defined in this way, for example. Given a random variable, this is the nth non-central moment of the random variable X. And according to our definition, in order to compute this expectation, we have to derive theoretically the distribution of X to the n, function X raised to the power of n. That's probability measure must be derived. However, according to the fundamental theorem, we don't need that. We just need to do what? X raised to the power of n and the density function of X dx. That's why I have given you the fundamental theorem first. Probably in your high school, middle school, even the undergraduate school, probability courses, in many cases, you will just say that, hey, okay, we compute the moments, X to the n, so it's X to the n, density X dx. No, okay? You need to prove or at least accept the fundamental theorem of expectation first. Anyway, this is the definition, you may say, or this is the obvious derivation, right? And we have a lot of things. And here goes the representative value again. So given a multiset, multiset of real numbers, we could find, or we wanted to find a representative value, right? And arithmetic mean, sometimes quadratic mean. Those means usually have the same unit as our members, right? Now, what about the moments? Definitely, if X has unit meters, then X to the n has the unit meters raised to the power of n. So if we keep the unit, then probably we want to put the nth root, right? Actually, that is the quadratic mean. So quadratic mean, the counterpart of quadratic mean is actually simply this one. Got it? And you can easily show that this is always greater than expectation of X. By the way, we compare two numbers. Then we already assume that their units are the same. As I told you, we cannot compare 500 milliliter cup with 1 liter cup, right? See that if X has unit in meters, the right-hand side also has unit meters. And this is the inequality. We already know quadratic mean is the greatest, and then arithmetic mean, geometric mean, harmonic mean, something like that, right? Anyway, so people really love these moments or kind of modified versions of moments. Why? Because it's easy to compute. As you see that we have polynomial, and polynomial is one of the simplest function to integrate. Of course, the simplest one is constant, right? But that's too simple. And then it would be a linear function. That's too easy because linear function ax plus b, then it's just, you don't need to compute anything except the expectation of x. So x to the n is really appealing. So those values are named as moments. Got it? And among moments, as I told you, there are around 3 things, actually 4 things. The first is that you have non-central moments and central moments. And also you have ordinary moments and absolute moments. So here, absolute means that, for example, you have combination. Absolute central means that you have x random variable minus its mean, denoted by x bar, raised to the power of n. I'm sorry, not that. You take the absolute value and raise it to n. Okay? Then, for example, this is called the nth order central absolute moment of random variable x. And I have my own story. When I was a middle school student, in one of my math class, professor started to talk about the variance or standard deviation. Probably you experience the same thing. And he said that the variance provides us how our samples are dispersed. Right? Makes sense. But I asked him, Professor, it's really strange you use this one. I would rather use, because we learned what is the absolute value, this one. What is this one, by the way? It is the first central absolute moment. And definitely that has what? The same unit as our sample. Why do we raise to the power of 2 and take the square root to have the same unit to get the standard deviation? So I kind of protested to my teacher, and I got punished. That was even though I was one of the best students in the entire second sophomore. Can you believe that? It doesn't matter where you are number 1 or 2. If just teacher have some gut, then you got punished. Anyway, he didn't answer at all. He just got angry because I guess he couldn't answer. Absolutely, because we use absolute value, this is okay. No one dare say that this is wrong and that is, after you take the square root, is correct. To represent the dispersedness of sample, you can use anything. Okay. However, as you already know, this is hard to compute. Whenever you have absolute value, probably you remember the killer problems in the entrance exam, right? 수능 killer problem. They all have Gauss function, absolute value functions. Forget. Okay. So we are really strongly motivated to use this function to define the dispersedness of our samples from the mean, rather than this first order absolute central moment. Got it? That must be a good answer, but he didn't answer in that way. Just he got a different kind of answer. Okay, anyway, so I just covered the moments and central moments and moments, ordinary moments and absolute moments, and you understand. Got it? By the way, this second order central moment is very, very useful in representing what? It's a representative value of the distribution. In what sense? It gives you a kind of amount of dispersedness, right? So people really love these two, mean and variance, sometimes mean and standard deviation. For the variance, we have notation sigma squared, because sigma is used as the standard deviation. So positive root of the variance is called the standard deviation. When we have two random variables, we specify whether the sigma square is the variance of random variable x or not. Sometimes I will prefer VAR of x to denote the variance of x. And since this is the expectation of some non-negative value, it's always non-negative. Remember this. Expectation equals what? Value times probability, summed, right? If the value is non-negative, then its sum must be non-negative because probability is always non-negative. So the variance is always non-negative. Obvious, right? An interesting thing about the variance is that unlike the expectation, because if you use the definition, you can easily show that A times X is A squared times variance of X. And if you add some constant to the random variable, its variance does not change. Really, the variance is about the dispersedness with respect to the center. One interesting lemma that appears usually only in graduate courses related to the mean and variance is this one. And this lemma also has counterpart in physics. Now you remember something like this. Whenever you swing something, what is the most important thing? Center of gravity. Why? Because if you hit something, if you hit that in so-called the sweet spot, then you can transfer the most power to that. Or when you rotate something, then what? It is the easiest to rotate some object around the axis passing through the center of mass, something like that, right? Why? Because it minimizes the rotational moment. If you swing here, it's easy, but if you swing here, it's difficult, right? Now, think about this question. Given a random variable x, and you consider a function of a. So a is a real number you want to choose. So if you change, you have a different number, right? Expectation of random variable minus, not baggy, minus constant squared, right? Now, minimize that g of a. Interestingly, this problem minimize, so arg mean of expectation x minus a squared equals x bar. This is actually what? Value squared times the weight. What is that? You remember from physics. So you find some point, and from this x minus a is the distance from a to x, right? And squared times the mass. What is that? Rotational inertia of moments, right? So when do you minimize the rotational inertia? When you pick that point as the center of mass. Same thing. Okay. So this is one thing. Now let's interpret this one. What does this mean? You minimize x minus a. So you have a random variable now. And now you want to guess what would be the outcome, right? And you may, given a Gaussian random variable, as you know already, you want to represent this entire distribution using a single number. It's impossible. However, you want to do that. And now your optimality criterion is what? The mean squared error minimized. See that? This is mean squared. What is that? Error, right? You want to minimize the mean squared error. So minimum mean squared error representation, or minimum mean squared error estimation in this case. What is your answer? You want to minimize the mean squared error by representing the entire distribution using a single number. It's the mean, okay? The mean value, the expected value of a random variable minimizes the mean squared error. Now, here goes better known example. Let's consider conditional minimum mean squared error. We can do that, right? Now, what would be the argument? The argument that minimizes this quantity. And many people got stunned because, oh, how can I compute? Forget about that. As I told you, this notation is simply that what? You originally had probability space. Now you derive a new probability measure. And that is what? That is a new experiment, random experiment, conditioned on the occurrence of event A. So forget about previous P. What would be that? It's the expectation of X given the occurrence of A. So naturally, your answer is what? X bar given A. No notation like that, so you write it this way. So conditional expectation is the MMSE estimate of your random variable. This is one of the key results you will be taught in the estimation and detection theory. Got it? Anyway, I really wanted to finish this part, and it seems I didn't. We have a big problem. Okay? Anyway, I'm talking too much, but I believe you are much better educated than you were when you were taking other courses, other undergraduate courses. So my plan is like this. Since we have still a lot to cover, right? As you see, a lot. We have more left than covered for this chapter. Is it chapter 3? Yeah. So anyway, I'm going to give you the homework covering up to today's lecture. And I will try to finish the rest of this chapter on Tuesday. So on Thursday, let's take our quiz covering up to this chapter 3. Got it? Is it chapter 2 or 3? Chapter 3? I believe so. Yeah, chapter 3. Got it? Yeah, there are a lot to go. Yeah, but I believe we've covered a lot. Okay, that's all for today.